Hey guys, just wanted to start doing a little preliminary physics lecture. I know that Dr. Haynes, before our spring break, had covered chapter 15, which was over mass, and it's my understanding that I was supposed to be doing chapter 16. But when I looked at the syllabus, the chapter titles are actually reversed, but we're still in line doing the correct chapter. Just the numbers were different. This is chapter 16, talking about KVP. And I just thought I'd do a few little different recordings. Maybe will help you out. And we will do a full lecture. I will do a full lecture tomorrow as scheduled. But I'm starting with chapter 16. We're talking about kilovolts KVP. And I just wanted to kind of flip over to the PowerPoint, which I normally don't do. But I thought it would be useful if I walk you through some of this. Let me get this content shared for you and see if I can get it going. Okay, so this is PowerPoint slides for radiography in the digital world, digital age, kilovoltage peak, and this is chapter 16. It says on page 249 in your book, it says they abbreviated KeV, kilo electron volts or kilovolts, a measure of the electrical force or pressure behind a current of electricity which causes it to flow. Sounds familiar. It should sound familiar to you. This is something that you're familiar with because we've talked about the circuit of the X-ray tube itself, and we know the force that's required to push those electrons across that tube comes from your applied kilovolt peak, kilovolts, created by the energy of any potential difference. Well, there is a potential difference that exists in the tube. As you know, we have the cathode and the anode, so they have opposite charges. So there is that potential difference. And there's also going to be this huge force that comes when we push our exposure switch all the way down. So that's going to really push that energy, causing that energy to be converted into kinetic energy as it interacts with the anode surface and creates your X-rays. So just keeping that in mind because this kind of plays off of that. The KVP control is actually the auto transformer in the X-ray machine circuit. Everybody remember that the auto transformer has one winding and it serves as both your primary and your secondary windings. So as you're setting your KVP, you're either using all of it or some of it. So that's how you get the different terms ratio. Whereas mass controls the quantity of the X-ray beam, quantity meaning number, meaning intensity. KVP controls the quality of the X-ray beam, how powerful, how penetrating is the X-ray. That's going to be very, very important that we keep that in mind. And again, I know Dr. Haynes talked about mass being quantity, being number. It has a direct relationship as far as patient exposure or image receptor exposure. As your mass increases, the exposure to the plate increases proportionally. Whereas with KVP, it does have an effect on the amount of X-rays being created. As we increase our KVP, we're actually creating more X-rays because we have more BRIMS interactions because of the higher KVP. So that in turn does affect the quantity. But the primary purpose of our KVP, our kilovolts, is the penetration of the beam. Keep that in mind. Okay, again on page 250, we're talking about a figure 16-1. It's talking about your peak and your average. And we know that the average energy of an X-ray beam, if we think about the emission spectrum, which I think there's a slide coming up, it will show you that even though we set a KVP, that's the peak. That's the highest energy any of your X-rays can have. But we know that the average energy equals to 1/3 of that set KVP. Again, this is off of that emission spectrum, and we've already had this discussion. But it says due to the constant fluctuation of KV for most types of X-ray machines, voltage measurements must be expressed as average or peak voltage reach. The main purpose for adjusting the kVp is to set the penetration level of the X-ray beam. The penetration of X-ray penetration through any particular tissue is a function of the average energy of the X-rays. So that bell, the top of your bell-shaped emission spectrum, those X-rays at 1/3 of that energy, where you have most of your X-rays being produced at that energy level, those are responsible for the penetration. That's where you have the majority of your X-rays, and it's that energy level that you're going to be interested in as far as penetration goes. And this is the emission spectrum. This was previously discussed. The effect of increasing kVp upon the X-ray beam spectrum is both to raise the average energy, moving the curve to the right. As you can see, it went from 80 to 90, moving the curve to the right, and it also slightly raises the curve due to more bremsstrahlung being produced, increasing the quantity of X-rays as well as the quality. So as we looking at this emission spectrum, as we see, we're going from the solid green line at 80 and the dotted green line at 90. We're increasing our average energy by 10. Our kVp, the peak, at 10. So we're going from 80 to 90. We can see that the amplitude of this curve is higher on the dotted line. So that means that the quantity has increased as well as it's shifting to the right as we've set our kilovolt peak by incremental change of 10. It says the increased output of the X-ray tube at higher kVps cannot be avoided and should be taken into account when considering the total exposure reaching the imaging receptor. What is that saying? That's telling us that as we increase our kVp, we have to keep in mind that both the quantity and the quality of the X-rays are increasing. So what Dr. Haynes talked about mass was directly related to only the number or the intensity of the X-rays. If you doubled your mass, you got twice as many X-rays. Well, here with kVp, not only are we making the beam more powerful, more penetrating, but we're also creating more X-rays, which is kind of a downside to this. We would prefer for it to only be affecting the penetrability and not necessarily the number of X-rays being produced. Now, mass is still your primary controller for the number of X-rays, and your kVp is still the controlling factor for penetrability. But as we increase our energy, our kVp, think about the interactions, the bremsstrahlung, they will have more opportunities to break multiple more times based on the higher energy. So each time they're able to break more, they're creating another X-ray. So yes, our number of X-rays are being increased, not proportionally like with mass, but they are being affected. As you can see that this graph, the dotted line, slightly goes up. And that area underneath each of those, the solid green line versus the dotted green line is higher, representing the total number of X-rays from all energy levels. So the energy level has increased to 90, and the dotted line tells us that the area underneath the bell-shaped curve has increased, so that is in quantity. So this is what this chapter is going to be talking about, is how kVp and mass can be adjusted so that you have the same output, because we have to take in consideration that as kVp is increased, it not directly increases the number of X-rays, but it does increase the number of X-rays to the point where we have to keep that in mind as we're going up in our kilovolt peak. In order to get the penetration, we're also getting more X-rays being produced. So sufficient penetration and subject contrast on page 250. The most important function of KVP is to provide at least partial penetration through all tissues to be recorded. If you look at these examples on the bottom of this slide, you can see the first one is that silhouette or that ghost-like image that I think Dr. Haynes has talked about in one of her lectures. That tells us that very few x-rays have gotten through, so that hand was actually under-penetrated. Okay, it was under-penetrated, and it tells you, this is on page 250, figure 16-2. It says on a conventional radiograph, A through E, and I think there's a little discrepancy. This one has G on it, but it still has the same idea. It says that with increasing mass, these are all taken at 30 kVp. We know as technologists and students that 30 kVp is not strong enough to penetrate. So as we're increasing it from 45 to 90 to 180 to 360 to even 720 mass, there is still no difference in penetration. We cannot see through the bones. There is still a substantial amount of unexposed anatomy. It's still got lots of white in it. So the details within the bones of the hand cannot be made out. And it shows you at on this particular slide, not in your book, but it says G, and I think in your book it says E, but G was taken at 54 kVp for comparison. So we can see that at 54 kVp, which is an appropriate exposure level as far as penetration goes, at 54, you can actually see what you're needing to do. So from 30 to 54, 54 definitely gave you the penetration, although it still looks like it's somewhat overexposed with mass because we still have a lot of the burned out fingertips. Okay, and again, that was on page 250. And going over from page 250 to 251, sufficient penetration and subject contrast. And it talks about, it says, as KVP increases, more different types of tissue are penetrated and recorded as shades of gray rather than blank white. Now, if you have blank white, you have total absorption of the beam. So there was nothing to be recorded on the image. Remember in radiology, we have no blacks and we have no whites. So if we have whites, that tells us that there was no penetration. All of the x-rays were absorbed by the photoelectric effect, and none got through to the image. So what we're shooting for is that we want to get recorded shades of gray rather than the blank white. At high KVPs, contrast agents such as barium can be penetrated to record details within the organs. And again, that's what contrast agents are used for, is to create contrast where otherwise there would be no inherent subject contrast. Since more information is present, it is generally desirable to have long grayscale in the image. And it says figure 16-3, number 4 to the right. You can see why there's a lot more grays. You can see a little bit of the lung markings. That's what we're after. We don't want that bright black and white like image number 1. We want number 4. So if that's a good thing to learn as we'll be talking about the chest and the abdomen. For the chest x-ray, we want a long gray scale of contrast. As many grays as possible when you're looking at the lung in the mediastinum, which is the middle area around the heart. And this gives you sufficient penetration and subject contrast. On page 252, there's a table in 16.1, and it tells you that the minimum KVP, this is the minimum for a particular body part, is defined as the lowest KVP that can still provide some degree of penetration through all tissues of interest. You're always going to try to penetrate the most dense part of the anatomy that you're imaging. So if you're doing a finger, obviously we have to have penetration through the bone. The bone has to have that trabecular pattern in order for us to say that it has sufficient penetration and that it shows good subject contrast. So again, keep in mind, this is the minimum KVP because it's going to go later on and it's going to tell us there's a different chart in the back part of the chapter that gives us the KVP for digital imaging, which you now know, or you should know by now, that we encourage higher KVPs. So these are good for film screen. These are good for CR. But when we get into the DR system, that is where it really wants us to incrementally change these KVPs to higher levels. So by adding at least a minimum of 10 for a hand, a wrist, or digits, we'd use 64 because the equipment, the digital system, prefers the higher energy. But this right now, we're talking about the minimum KVP for a particular body part is defined. And know that by definition, what's the minimum KVP? There's going to be an optimal KVP, but this is the minimum. This is the least amount of KVP that you can use to ensure that you have gotten penetration through the anatomy and you have stretched out that scale of contrast as far as you can go with it. Sufficient penetration and subject contrast. Here I've already mentioned this, but it says note that higher optimal KVPs are recommended in table 16.3 for digital imaging. 16.3 is actually on page 258, and that is for the digital. And notice here, if I can back up, look at the hands and wrists. It says 54. Okay, I'm sorry, I'm going the wrong way. This again is showing you the same chart that was on page 252, but if you compare it to the one on page 258, look for the hand, wrist, and digits. It's got 64 instead of 54. So it's telling you that the digital imaging systems prefer to use higher KVPs. That's a plus for us, and with patient exposure, we'll get in that in just a minute. So that's talking about KVP to ensure that we have good penetration. We're wanting a long scale of contrast. That is radiology. We're always trying to stretch our contrast out to the point where we got a lot of grays. We always want to make sure that we've penetrated the thickest part of the anatomy being imaged, that normally being the bone. We want to penetrate through the bone. If the bone turns out to be blank white, that still tells us that we have not used the minimum KVP required for that exam. Okay, sufficient penetration and subject contrast. The penetration required to determine by the predominant type of tissue in the body part. This is on page 251, and this is kind of what I've already said. It's giving you an example talking about the male patient. The lateral thickness of the waist and hips is typically the same for males. It says the lateral thickness of the waist and hips is typically the same, yet 8 to 12 kVp more is often used for the lateral spot view of the L5-S1 than for the routine lateral L-spine. Guys, I know we haven't covered the spine yet, but what that's talking about, there's actually a spot called junction of the L5-S1. That's where your lumbar and your sacrum connect in your spine. And when you're doing a lateral of that, you have to remember there's two pelvic wings right exactly where the L5-S1 junction is located. So that is a very, very thick part of any patient in a lateral spine. So when we're doing the L5-S1 cone down, we're coning down, collimating just to that, we're penetrating nothing but bone. So we definitely have to increase penetration there. We have to ensure, and that's by increasing it by 8 to 12 kVp. Is that really important at this point? No. But you will learn this in positioning in the fall when we get into positioning too and talk about the spine, that you do have to go up as you turn your patient from an AP to an oblique to a lateral. You are increasing, if nothing else, soft tissue, so that you still have to go up in your technique just a little bit to, again, ensure that you're having that penetration. It says the lateral L-spine is about 20% bone and 80% soft tissue. The lateral pelvis contains about 40% bone and 60% soft tissue. So that lateral pelvis, that's what you're going to be shooting through when you're getting that L5-S1 junction image on a L-spine series. So that is going to require, again, 8 to 12 kVp more. So on page 252, it talks about sufficient penetration and subject contrast. This is kind of redundant, but we're going to say it one more time. When penetration is insufficient, no amount of radiation intensity can ever compensate. Subject contrast remains excessive. So what is that telling us? When penetration is insufficient, no amount of radiation intensity. So we know the word intensity should now tell us that we're talking about mass, can ever compensate, and your subject contrast remains excessive. So regardless what mass you use, whether it's 10, 20, 30, or 40 mass, if you're underpenetrated, you're still underpenetrated, because you haven't increased the penetrability of the beam by increasing your KVP. So your KVP has to be there. You have to have sufficient penetration before you can start changing your mass. Mass cannot compensate. Mass is nothing but the number of x-rays, not how penetrating the beam's going to be. That is controlled by your KVP. When KVP is sufficient, the percentage of penetration remains the same at any amount of mass. So that's telling you the opposite. Once you have penetration, you can't get any more penetration by changing mass. So mass only controls the number of x-rays. How far the x-rays actually travel through the body is completely controlled by your set KVP. And of course, the amount of the amount of x-rays coming to your image receptor controls your overall level of contrast, your scale of contrast. So the more that can actually get through, the more longer scale of contrast you're going to have. But if they don't get through, you can't compensate for underpenetration by increasing mass. That's the gist of this. That's what you have to remember. You cannot compensate for underpenetration. You cannot change your subject contrast by changing your mass. It has to be your KVP. All right, guys, this is where the 15% rule is going to come into play. And I am going to actually stop here. I'm going to stop sharing my screen. I am going to stop this recording. I'm going to pick this up and have this 15% rule as a separate video, which I'll do later this afternoon. You guys have a test today. But I do want to pick this up and do it in small incremental bites so it won't be so overwhelming to you. But again, that talks about your KVP, your penetrability, what KVP does to the actual production of x-rays. As you're increasing your KVP, remember what it does in the tube. It's the force, it's the push. As you're increasing that push, that potential difference changes and you're getting more. So as it travels through the tube and hits the anode surface, it's going to have that more Bremsstrahlung interaction. So therefore, if you got more Brems interactions, or reactions as I call it, you have more x-rays being produced. So KVP will affect the number of x-rays being produced within the tube. Now, whether or not that changes them, those x-rays, because remember it's polyenergetic, doesn't mean that we're going to get more of them that will penetrate through the anatomy, because that's not necessarily true. All we're trying to do is get optimal KVP to penetrate the anatomy. And we just have to go with the idea that there will be more x-rays produced at all energy levels. But we know that what happens to some of that gets filtered out. Some of that will be absorbed by the body part itself. They won't get through the body. So what hits the image receptor are going to be those that we've actually given the penetration as we've increased our KVP. So as we've increased our KVP, two different things happen. There's more x-rays being produced because of the Brems interaction. And we've also increased our penetrability of the beam to the image receptor. So those are two things that we'll talk about, and we're going to have to figure out a way to balance those two as we increase one, we're going to have to do something to the other technical factor. These two technical factors, of course, are KVP and mass. So this is the end of part one. I'll pick up on part two probably this afternoon, and I will get these posted to you. And again, watch them if you'd like, or you can wait on our actual lecture. All right, thanks, guys.